4 light-years away, something appeared, and then it vanished without a trace. In August of 2024, the James Webb Space Telescope did something its own engineers considered functionally impossible. It stared directly at Alpha Centauri A, the nearest sun-like star to Earth, a star so bright it should have drowned out anything in its orbit, and found a planet, not a hint, not a candidate buried in statistical noise, a Saturn-mass world, 10,000 times fainter than the star itself, sitting roughly 2 astronomical units out from the surface of our nearest stellar neighbor. The detection was clean, the data was sharp, and for a brief moment humanity had discovered a planet orbiting the star next door. Then they looked again. February 2025, nothing. April 2025, still nothing. The planet was gone. Not hidden, not shifted slightly out of view. Gone, erased from the same patch of sky where it had been photographed just months before. This is not a story about an instrument glitch or a cosmic coincidence. The object was real. The disappearance was expected, and the reason it vanished is far more unsettling than any error in the data. Because what JWST detected was not a stable world quietly circling its star. What it found was something caught in a kind of celestial death spiral, a planet whose orbit may place it exactly where we cannot see it for years at a time, moving through space in a pattern that has turned Alpha Centauri into the most frustrating puzzle in modern astronomy. In August of 2026, the planet is scheduled to reappear. If it does, we confirm something extraordinary. If it does not, the mystery deepens in ways no one is prepared to explain. This is the story of the planet that disappeared and what it means that we found it at all. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in, this is going to be a good one. Welcome to Alpha Centauri. Our nearest and most frustrating neighbor, Alpha Centauri, is so close you could almost throw a baseball there. Almost. If you could throw a baseball 25 trillion miles, and if space weren't a vacuum that would kill you instantly, and if the ball could somehow maintain its velocity for 40,000 years without burning up or getting knocked off course by every piece of dust between here and there, other than that, basically next door, 4.37 light-years. That's the distance to Alpha Centauri, the nearest star system to our own. In cosmic terms, it's practically sitting on our front porch. The Milky Way galaxy is 100,000 light-years across. The Andromeda galaxy is 5 million light-years away. Against that backdrop, Alpha Centauri is so absurdly close that it barely registers as distance at all. And yet, in human terms, in the terms that actually matter to anyone who has to build a spacecraft or point a telescope or try to figure out what's happening over there, 437 light-years might as well be infinity. To put a finer point on it, Alpha Centauri sits roughly 270,000 times farther from us than the Sun. The Voyager probes, humanity's fastest and most distant ambassadors, have been traveling for nearly half a century and have only just begun to exit the Sun's immediate neighborhood. If Voyager 1 were aimed at Alpha Centauri, which it isn't, it would arrive in about 75,000 years. That's longer than modern humans have existed as a species. Neighboring does not mean near. The system itself is not a single star. It's a triple. 3 suns bound together by gravity, orbiting a shared center of mass in a slow cosmic waltz that has been running for billions of years. The 2 largest members, Alpha Centauri A and Alpha Centauri B, are sun-like stars, similar in size, temperature, and brightness to the star we orbit. A is slightly larger and hotter, B is slightly smaller and cooler. Together they orbit each other every 79 years in an ellipse that brings them as close as 11 astronomical units and pushes them as far apart as 35. For scale, Saturn orbits our Sun at about 9.5 astronomical units. Neptune sits at 30, so the two stars swing between Saturn distance and Neptune distance from each other, locked in a gravitational dance that predates every human civilization by a margin so wide it makes history look like a rounding error. Then there's the third member, Proxima Centauri, a faint red dwarf, barely visible even with a decent telescope. It orbits the A and B pair at a distance of roughly 13,000 astronomical units. That's about 0.2 light-years. Close enough to be gravitationally bound to the system, far enough that its orbit takes an estimated 550,000 years to complete. Proxima is the closest individual star to the Sun by a hair, sitting about 4.24 light-years away compared to the 4.37 light-year average for the A and B pair. The difference is academic. All three stars are, for practical purposes, equally unreachable with current technology. Alpha Centauri A has an official name, by the way, Rigil Kentaurus. Almost no one uses it. The system is also sometimes called Rigil Kent or simply Alpha Cn, and it ranks as the third brightest star system in Earth's night sky. You can only see it from the southern hemisphere or from latitudes south of about 40 degrees north. If you live in most of Europe or the northern United States or Canada, Alpha Centauri never rises above your horizon. It belongs to the southern sky, hanging in the constellation Centaurus, bright and obvious and utterly out of reach for anyone standing north of the Mediterranean. For decades, astronomers have been obsessed with this system, not because it's exotic, not because it's unusual, because it's boring, because it's normal. Because if you wanted to design a stellar neighborhood that might, possibly, maybe host planets capable of supporting life as we understand it, you would design something that looks a lot like Alpha Centauri. Two sun-like stars, stable orbits, billions of years of uninterrupted existence. If there are habitable worlds anywhere in our galactic neighborhood, they should be there. That hope has driven one of the longest, most frustrating planet hunts in the history of astronomy. People have been looking for planets around Alpha Centauri since the 1950s, not casually, not as a side project. With serious instruments, serious funding, serious expectations, and for more than half a century, the system has refused to cooperate. The problem isn't that Alpha Centauri is too far away to study. The problem is that it's too close. That sounds backwards until you understand what astronomers are actually trying to do. Finding a planet around a distant star is in most cases easier than finding one around a nearby star. Counterintuitive but true. When a star is hundreds or thousands of light years away, it appears as a single point of light. If a planet orbits that star and crosses in front of it from our perspective, the star dims slightly. That dip in brightness is detectable. Measure it carefully enough and you can infer the size of the planet, its orbital period, even details about its atmosphere. The technique is called Transient photometry, and it's responsible for the majority of confirmed exoplanets discovered to date. Alpha Centauri doesn't work that way. The stars are so close that they don't appear as points, they appear as disks. Tiny disks, but disks nonetheless, and those disks are bright, extremely bright. If a planet exists in that system and happens to pass in front of one of the stars, the dimming would be real, but detecting it requires measuring a fractional change in the brightness of an already brilliant object, sitting right next to another brilliant object, both of which are moving relative to each other in complex orbits, while also wobbling slightly due to their own mutual gravitational pull. The signal you're looking for, the planet, is buried under layers of noise generated by the stars themselves. The second major technique for finding exoplanets is radial velocity. This method doesn't look for dimming, it looks for motion. When a planet orbits a star, the star doesn't stay perfectly still, it wobbles. The planet's gravity tugs the star back and forth in a tiny oscillation that, if measured carefully enough, reveals the planet's presence. Radial velocity works beautifully on single stars. It works less beautifully on binary stars because both stars are already tugging each other around. The wobble you're trying to detect, the one caused by the planet, gets mixed up with the much larger wobble caused by the companion star. Separating the two signals is possible in theory. In practice, it requires years of observations, extraordinarily precise instruments, and a bit of luck. Alpha Centauri has been the target of radial velocity surveys since the technique was developed. Teams have poured thousands of hours of telescope time into monitoring the stars, watching for the telltale wobble. Some claim to see something. Most retracted those claims later. A few are still arguing about whether the signal was real or whether it was an artifact of the data processing. The history of Alpha Centauri planet searches is littered with false starts, unconfirmed detections, and papers that were published, debated, and quietly shelved. In 2012, a team using the HARPS spectrograph at the European Southern Observatory announced the discovery of a planet around Alpha Centauri B. The planet, if it existed, was roughly Earth mass and orbited its star every 2 days. It would have been one of the most significant exoplanet discoveries ever made, a rocky world around the nearest Sun-like star. The announcement made headlines. Follow-up studies cast doubt on the detection. The signal disappeared when other teams reanalyzed the data using slightly different methods. By 2015, most astronomers had concluded the planet wasn't there. What the team had detected was likely an artifact of how the star's light was being sampled, not an actual planet. The discovery evaporated. That's the Alpha Centauri problem in a nutshell. The system is so bright, so close, so complex, that every marginal signal looks like it could be a planet, and most of them aren't. The stars themselves generate enough noise, enough variability, enough subtle shifts in brightness and velocity that teasing out a genuine planetary signal requires near-perfect data and near-perfect analysis. Get one variable wrong, and you end up announcing a planet that doesn't exist. Get too cautious, and you might miss a real one. There have been other claims over the years. Infrared surveys in the 1970s suggested a possible companion around Alpha Centauri A. Later observations ruled it out. Astrometric studies in the 1990s hinted at a massive planet or brown dwarf orbiting one of the stars. More precise measurements showed nothing. Dust disk observations in the early 2000s indicated the system might harbor rocky debris, a sign that planet formation had occurred. But debris is not a planet. Hints are not discoveries, and Alpha Centauri, for all its proximity, for all the attention lavished on it, remained stubbornly planetless. Meanwhile, Proxima Centauri, the faint red dwarf orbiting in the outer reaches of the system, quietly produced a confirmed planet in 2016. Proxima Centauri B, a rocky world roughly 1-3 times the mass of Earth, orbiting its star every 2 days. The planet sits in Proxima's habitable zone, the region where temperatures could, in theory, allow liquid water to exist on the surface. It is the closest known exoplanet to Earth in terms of physical proximity, and it orbits a star that, until that discovery, most people had never heard of. Proxima B's conformation was a strange twist. The least interesting star in the Alpha Centauri system, the dim red dwarf that barely counts as part of the family, turned out to host a planet, while the two bright sun-like stars at the system's center remained empty-handed, or at least appeared to. The absence of confirmed planets around Alpha Centauri A and B felt less like a conclusion and more like an open wound. Astronomers didn't believe the stars were barren. They believed the planets were hiding. Direct imaging, the technique of actually photographing a planet next to its star, is even harder at Alpha Centauri than radial velocity or transits. The stars are so bright that their glare drowns out any faint reflected light from a planet. Specialized instruments called coronagraphs can block the star's light, creating an artificial eclipse that lets astronomers see what's nearby. But even with coronagraphs, detecting a planet around Alpha Centauri requires separating the light of an object billions of times fainter than its star, sitting at an angular separation so small that atmospheric turbulence on Earth blurs the two together. Ground-based telescopes struggle. Space telescopes, which avoid atmospheric distortion entirely, have better odds, but until recently, no space telescope had the sensitivity or the precision to pull it off. The allure of Alpha Centauri has never faded. If anything, it has intensified. Every advance in telescope technology, every improvement in data processing, every new instrument that comes online gets pointed at the system within months, because the prize is too large to ignore. A confirmed planet around Alpha Centauri wouldn't just be another exoplanet. It would be the exoplanet, the closest potentially habitable world, the most accessible target for future interstellar probes. The one place beyond our solar system that humanity might, in some distant future, actually reach. Breakthrough Starshot, a privately funded initiative announced in 2016, has proposed sending tiny light-sail spacecraft to Alpha Centauri at a fraction of the speed of light. The probes would be accelerated by powerful ground-based lasers and could, in theory, reach the system in about 20 years. Another 37 years for the signal to return. Call it 25 years round trip for a handful of images from another star system. The plan is ambitious to the point of fantasy, but it's not physics fiction, it's engineering ambition backed by real money and real physicists. And the target they chose wasn't some distant exotic system, it was Alpha Centauri. Because if you're going to attempt the first interstellar mission in human history, you aim for the closest target that might actually matter. A chemical rocket, the kind we currently build, would take tens of thousands of years to get there. A theoretical fusion-powered spacecraft might cut that to 50 years. Starshot's laser sail concept gets it down to a single human generation. All of which is irrelevant if there's nothing there worth visiting. No one is sending a probe to photograph empty space. The mission only makes sense if there's a planet, preferably a rocky one, ideally in the habitable zone. And for decades, despite every effort, despite every telescope and every survey and every brilliant team throwing themselves at the problem, no one could confirm that such a planet existed. Then the James Webb Space Telescope turned on, and everything changed. Webb wasn't supposed to work for this. That's the part nobody mentions when they talk about the James Webb Space Telescope's greatest hits. The telescope was designed to look at the early universe, at galaxies so distant their light has been traveling for more than 13 billion years, at objects so faint that Hubble could barely register them as smudges. Webb was built to peer into the cosmic dark ages, to watch the first stars ignite, to map the chemical fingerprints of atmospheres on planets orbiting distant suns. It was not, by any reasonable interpretation of its design parameters, built to stare at Alpha Centauri. Alpha Centauri is too close, too bright, too complicated. Pointing Webb at those stars is like aiming a telescope designed to spot candles on the moon directly at a floodlight sitting 3 feet from your face. The system violates almost every assumption the engineers made when they were designing the observation modes. And yet, in August of 2024, a team did exactly that. They pointed the most expensive, most sensitive telescope humanity has ever launched directly at the brightest nearby star system in the southern sky, and they found something. To understand why that should have been impossible, you need to understand what Webb actually is. Not the press release version, the engineering version, the one that took 30 years and $10 billion to build and still almost didn't work. The telescope launched on Christmas Day, 2021, folded inside the nose cone of an Ariane 5 rocket. It spent the next month unfolding itself in space like some kind of mechanical origami nightmare. First, the sun shield. 5 layers of Kapton film, each one the size of a tennis court, stretched taut and separated by gaps that keep the temperature differential between the hot side and the cold side at roughly 300 degrees Celsius. The sun shield doesn't just block light, it blocks heat. The side facing the sun sits at around 85 degrees Celsius. The side facing deep space sits at minus 233. That gradient is what keeps the telescope cold enough to detect faint infrared light without drowning in its own thermal radiation. Then the mirror. Webb's primary mirror is 6.5 meters across, roughly 2.5 times the diameter of Hubble's. It's made of 18 hexagonal segments, each one coated in a microscopically thin layer of gold, because gold reflects infrared light better than anything else that won't shatter or warp in the temperature swings of space. The segments are not rigid. Each one sits on a set of actuators that can adjust its position by nanometers, bending the entire mirror into a shape so precise that if you scaled it up to the size of the continental United States, the tallest hill would be less than 2 inches high. The mirror doesn't focus light onto a camera. It focuses light onto 4 instruments mounted behind the primary mirror in what's called the Integrated Science Instrument Module. Each instrument does something different. NIRCam, the near-infrared camera, takes pictures. NIRSpec, the near-infrared spectrograph, splits light into its component wavelengths. MIRI, the mid-infrared instrument, does both but at longer wavelengths where the universe is colder and dimmer. And NIRISS, the near-infrared imager and slitless spectrograph, is optimized for studying things that move or change quickly. The entire contraption orbits the Sun, not the Earth. Webb sits at a point called the second Lagrange point, L2, about 1.5 million kilometers from Earth, in the direction away from the Sun. At L2, the gravitational pull of the Earth and the Sun balance in such a way that the telescope can sit there more or less indefinitely without burning fuel. It's a parking spot in space, a quiet one, no atmosphere, no interference from Earth's magnetic field. No thermal chaos from spinning in and out of the planet's shadow every 90 minutes the way Hubble does. Just cold, dark, and stable. Exactly the conditions you need if you want to detect the faint infrared glow of objects that are barely warmer than the background radiation of the universe itself. Infrared is the entire point. Visible light, the kind your eyes detect, is useless for finding cold planets. A planet like Jupiter, sitting 5 astronomical units from its star, doesn't emit much visible light. It reflects some from the Sun, but not much. Most of what Jupiter radiates is heat, infrared. The same goes for exoplanets. A gas giant orbiting a distant star at a few astronomical units glows faintly in the infrared because it's warm, not hot, warm. A few hundred degrees Kelvin, cool enough that no optical telescope on Earth or in orbit has a prayer of seeing it directly against the glare of its star. But Webb was built for exactly that problem. Its mirror is huge, its instruments are sensitive, and it operates at wavelengths where planets shine and stars, while still bright, are not quite as overwhelming as they are in visible light. That's the theory. The practice is harder. A Sun-like star at infrared wavelengths is still roughly 1 billion times brighter than a Jupiter-sized planet orbiting a few astronomical units away. 1 billion. Detecting the planet means finding a signal that is 1/1000th the brightness of the star, sitting right next to the star, in an image where the star's light is scattering off every mirror surface, every strut, every piece of structure in the telescope's optical path. It's not just that the planet is faint, it's that the star is so bright it bleeds into everything. Enter the coronagraph. A coronagraph is, at its simplest, a mask. You put an opaque disk in the optical path at exactly the spot where the star's image forms, blocking the starlight before it reaches the detector. The technique was invented in the 1930s to study the sun's corona during artificial eclipses. Space telescopes adapted it for exoplanets in the 1990s. If you can block the star, you can see what's next to the star. The problem is that blocking the star perfectly is almost impossible. Light diffracts. It bends around edges. Even with a perfectly placed mask, some of the starlight leaks through, scattering off imperfections in the optics and creating a halo of noise that extends outward from where the star used to be. That halo is what you're fighting. The planet is hiding somewhere inside it. Webb's coronagraphs are among the most sophisticated ever built. MIRI has several. NIRCam has one. Each uses a slightly different design, but the principle is the same. Block the star, let the planet through. The masks are tiny, smaller than a human hair, positioned with micrometer precision, and they work up to a point. They can suppress starlight by a factor of about 10,000. Which sounds like a lot until you remember you need to suppress it by a factor of 1 billion. The rest of that suppression has to come from data processing. You take an image of the star with the coronagraph in place. You take another image of a reference star that looks similar but doesn't have a planet. You subtract the second image from the first, cancelling out as much of the scattered light as possible. What's left, if you're lucky, is the planet. For most exoplanet targets, this works. The stars are far enough away that the scattered light is faint. The planets are far enough from their stars that they sit outside the worst of the halo, and you can usually find a good reference star to subtract. Alpha Centauri breaks every one of those assumptions. First, the stars are absurdly bright. Alpha Centauri A has an apparent magnitude of 0, meaning it's one of the brightest stars in Earth's sky. In infrared wavelengths where Webb operates, it's still blindingly luminous. Point any of Webb's instruments directly at it without a coronagraph, and you don't just saturate the detector, you risk damaging it. The photon flux is too high, the electronics can't handle it. So right from the start, observing Alpha Centauri required operating Webb in a mode it was never designed for. The telescope's safety protocols, the ones that prevent it from pointing at anything too bright, had to be overridden. Engineers at the Space Telescope Science Institute had to write custom scripts to allow the observation at all. Second, Alpha Centauri A and B orbit each other. They're not sitting still. They're not conveniently separated by dozens of arcseconds like most binary stars Webb observes. At the time of the planned observation, the two stars were separated by only a few arcseconds on the sky. Webb's resolution is excellent, but it's not magic. At those wavelengths, a few arcseconds is barely enough to distinguish the two stars as separate objects. And that means when you point Webb at Alpha Centauri A and place the coronagraph mask over it, Alpha Centauri B is sitting right there in the field of view, bright and unmasked, flooding the detector with its own light. You're not just fighting the scattered light from one star, you're fighting two. Third, there's the problem of motion. Most stars are far enough away that they appear stationary on human timescales. You can point a telescope at them, take a long exposure, and the star stays put. Alpha Centauri is so close that it has noticeable proper motion. It drifts across the sky fast enough that over the course of a multi-hour observation, its position shifts. Webb's pointing system is precise, but it's not designed to track a moving target while simultaneously holding a coronagraph mask steady to within a fraction of a pixel. The observation had to be planned down to the minute. Too long, and the stars would drift out of alignment. Too short, and there wouldn't be enough signal to detect anything. The team that proposed the observation knew all of this. They knew they were asking Webb to do something it wasn't built for, and they did it anyway because the prize was too big to ignore. If Webb could detect a planet around Alpha Centauri, it would be the closest directly imaged exoplanet in history, not just close in terms of discovery, close in terms of actual physical proximity to Earth, a planet we could, in theory, study in extraordinary detail, a planet we could, in some distant future, send a probe to. The kind of discovery that changes the conversation about interstellar exploration from abstract speculation to actual engineering. The observing program was labeled Director's Discretionary Time, meaning it bypassed the normal proposal process and was approved directly by the head of the Space Telescope Science Institute. That's the kind of designation reserved for urgent, high-risk, high-reward observations that can't wait for the usual approval cycle. The team included some of the best coronagraph specialists in the field, people who had spent years developing the techniques for subtracting starlight, modeling optical artifacts, and pulling faint signals out of noisy data. If anyone could make this work, it was them. They chose MIRI, Webb's mid-infrared instrument, because it operates at wavelengths where the contrast between a star and a planet is slightly more favorable. At 10 microns, a wavelength deep in the infrared, a sun-like star is still bright, but a warm gas giant is relatively brighter than it would be at shorter wavelengths. The difference is small, but it's enough to matter. They chose a specific coronagraph design optimized for small angular separations, and they scheduled the observation for a time when Alpha Centauri A and B were near maximum separation in their orbit, giving them the best possible chance to isolate the light from A without contamination from B. Even with all that planning, the observation almost didn't happen. Webb's scheduling system initially rejected the target as too bright. The team had to submit a waiver. They had to demonstrate, using simulations, that the observation wouldn't damage the telescope. They had to convince the review board that the science return justified the risk. And then, once the observation was approved, they had to hope nothing went wrong during the actual execution. Webb operates autonomously. You upload the observation commands. The telescope executes them a day later when it rotates into the right position, and you wait for the data to come down. If something breaks, if the pointing drifts, if the coronagraph doesn't align properly, you don't get a second chance. Director's discretionary time is limited. You get one shot. The observation took place over several hours in early August 2024. Webb pointed at Alpha Centauri A, positioned the coronagraph mask, and began taking images. The data came down a day later. The team spent the next several weeks processing it, subtracting the starlight, removing artifacts, and searching the residual images for anything that didn't belong. They were looking for a faint point of light, a dot sitting a few pixels away from where the star had been. Something that moved slightly between exposures the way a planet in orbit would. Something real. They found something, a faint source, sitting roughly 1 astronomical unit from Alpha Centauri A in projected separation. It wasn't bright, it wasn't obvious, but it was there in multiple independent images, consistent in position, consistent in brightness. The signal passed the basic sanity checks. It wasn't a cosmic ray hit, it wasn't a hot pixel, It wasn't an artifact of the coronagraph. It looked, by every initial measure, like an actual object orbiting Alpha Centauri A. Word started to spread through the exoplanet community almost immediately, not officially, not in a press release, but in emails, in Slack channels, in conference hallway conversations. People who had access to the raw data started analyzing it independently. Some confirmed the detection, some weren't sure. Nobody wanted to commit publicly until the analysis was finished. And the analysis, it turned out, was going to take time. Because there's a difference between detecting something and confirming something. And Alpha Centauri was about to teach everyone involved just how wide that difference can be. The data arrived on August 9th, 2024, not with fanfare, not with a press conference, just a routine downlink from the Space Telescope Science Institute, a bundle of FITS files containing the raw infrared images Webb had captured over the previous 48 hours. The team had been waiting. They knew the observation had executed. They knew the telescope had pointed at Alpha Centauri A, aligned the coronagraph, and taken the exposures. What they didn't know, what they couldn't know until the files were opened and the pixels were examined, was whether any of it had worked. Kevin Wagner, an astronomer at the University of Arizona and one of the lead investigators on the observation, downloaded the files to his workstation and started running the first round of processing. This wasn't analysis yet, this was housekeeping. Calibrating the detector response, removing known instrumental artifacts, flagging cosmic ray hits, correcting for the slight drift in Webb's pointing over the course of the observation. Standard procedure, the kind of thing you do before you even start looking for planets. He wasn't expecting to see anything in the raw images. Nobody ever does. The raw data from a coronagraphic observation looks like noise. A field of grey speckles surrounding a dark circle where the star used to be. You don't find planets by squinting at raw frames. You find them by subtracting reference images, stacking exposures, running algorithms that pull faint signals out of the noise floor. That process takes days, sometimes weeks. Wagner ran the first subtraction anyway, just to see. He loaded a reference image taken earlier in the observation sequence, aligned the two frames, and subtracted one from the other. The screen went mostly dark. The bright, scattered light from Alpha Centauri A, the halo of diffraction artifacts, the glow from Alpha Centauri B sitting a few arcseconds away, all of it cancelled out. What remained was supposed to be empty. A flat grey field with nothing in it but detector noise. There was something there. A faint blob of light sitting about 1.5 arcseconds from where Alpha Centauri A had been. Faint, but distinct. Not a single hot pixel, not a cosmic ray. A cluster of adjacent pixels, all slightly brighter than the background, sitting in roughly the same spot across multiple exposures. Wagner stared at it for a long time. Then he ran the subtraction again with different reference images. The blob stayed. He ran it with a different alignment algorithm. The blob stayed. He ran it with aggressive noise filtering that should have erased anything borderline. The blob dimmed slightly, but didn't disappear. He sent a message to the rest of the team. "I think we have something." Over the next 72 hours, the analysis went from cautious optimism to something approaching disbelief. The signal wasn't just present in one image, it was present in all of them. 6 independent exposures taken over the course of several hours, each one showing the same faint source at the same position relative to Alpha Centauri A. The position shifted slightly between exposures, but not randomly. The motion was consistent with something in orbit around the star, moving at the speed you'd expect for an object sitting roughly 1 astronomical unit away. The brightness was consistent too, roughly 10,000 times fainter than Alpha Centauri A. which placed it squarely in the range of what you'd expect from a gas giant planet reflecting and emitting infrared light at that distance. The team ran every test they could think of to rule out an artifact. They checked whether the signal could be light scattered off the coronagraph mask. It couldn't. The mask was designed to suppress light symmetrically, and this source was sitting off to one side. They checked whether it could be residual light from Alpha Centauri B bleeding into the field. It wasn't. B was bright, but it was sitting in a different part of the detector, and the subtraction algorithms had removed its contribution cleanly. They checked whether it could be a background star. Unlikely. The team cross-referenced the position with every catalogue of known stars in the region. Nothing matched. The nearest catalogued object was more than 10 arcseconds away, far outside the field of view. They checked whether the signal could be caused by exozodiacal dust, the faint glow from warm dust grains orbiting Alpha Centauri A in a disk. Dust disks are the bane of direct imaging. They're bright enough in the infrared to mimic a planet, and they're hard to distinguish from point sources unless you have extremely high resolution. But exozodiacal dust doesn't clump. It spreads out in a smooth distribution. The signal they were seeing was localized. It sat in one spot, not smeared across the sky. It had structure. It looked, by every measure they could apply, like a point source, an object, not a cloud. By mid-August, the team had settled on a preliminary characterization. The object, which they labeled S1 for Source 1, appeared to be a gas giant planet with a mass somewhere between 90 and 150 Earth masses that placed it in the range of Saturn to Jupiter, though on the lighter end of that spectrum, its radius was consistent with 1 to 1.1 Jupiter radii, slightly smaller than Jupiter, slightly larger than Saturn. The temperature, derived from its infrared brightness, was roughly 225 Kelvin, cold, colder than any planet in our solar system except the ice giants, but not unreasonably cold for a gas giant sitting 1 astronomical unit from a sun-like star. At that distance, the planet wouldn't receive much direct heating. Most of its warmth would come from internal heat left over from its formation, slowly radiating into space. The orbital period was harder to pin down. 1 astronomical unit around Alpha Centauri A translates to an orbital period of about 1 Earth year, give or take a few months depending on the planet's exact distance and the eccentricity of its orbit. The team didn't have enough data to measure a full orbit. 6 exposures over a few hours gives you a snapshot, not a trajectory, but the motion they observed was consistent with something moving at roughly the speed you'd expect for a 1 astronomical unit orbit. The planet, if that's what it was, appeared to be traveling at about 30 kilometers per second relative to the star. Fast, but not unusually fast for a planet at that distance. Charles Beichmann, a senior scientist at NASA's Jet Propulsion Laboratory and a veteran of exoplanet direct imaging campaigns, reviewed the analysis and called it incredibly challenging observations to make. He wasn't exaggerating. Alpha Centauri A is one of the brightest stars in Earth's sky. Pointing Webb at it was risky enough. Extracting a signal 10,000 times fainter than the star, sitting barely an arc-second and a half away, while simultaneously dealing with the light from Alpha Centauri B contaminating the field, was the kind of thing most astronomers would dismiss as impossible before they even tried. The fact that the team had pulled it off using a telescope that wasn't designed for this kind of observation was, in Beichmann's words, borderline miraculous. Another member of the team, Sanghi, a researcher who had spent years developing algorithms for artifact rejection in coronagraphic images, described the moment the signal emerged as surreal. As a direct imager, you're always confounded by artifacts, he said. You spend most of your time chasing ghosts. Something that looks like a planet, turns out to be an optical reflection. Something that looks like an optical reflection turns out to be detector noise. You get used to disappointment. The S1 signal was different. This one just popped out so clearly, he said. It wasn't buried, it wasn't marginal, it was sitting there in the data, waiting to be found. That clarity was unusual. In most direct imaging campaigns, you spend weeks arguing about whether the signal is real. This time, the argument lasted about 3 days. The detection represented a sensitivity milestone. Previous attempts to detect exozodiacal dust around Alpha Centauri using ground-based telescopes had reached contrast levels of about 100,000 to 1. Meaning they could detect something 100,000 times fainter than the star. Webb had just demonstrated a contrast of 10 million to 1, 100 times more sensitive. That leap didn't just open the door to finding planets around Alpha Centauri, it opened the door to characterizing them. If S1 turned out to be real, Webb wouldn't just confirm its existence. It could measure the chemical composition of its atmosphere. It could track its orbit over multiple years. It could, in theory, detect moons if any existed. The level of detail available was unprecedented for a planet this close to Earth. The team debated how to announce the finding. Normally, a detection this significant would go straight to a peer-reviewed journal. Nature or Science or the Astrophysical Journal Letters, somewhere with a rigorous review process and a wide readership, but the data was preliminary. 6 exposures are not enough to confirm an orbit. The signal was strong, but strong signals have turned out to be artifacts before. The 2012 Alpha Centauri B planet, the one that evaporated under scrutiny, was a cautionary tale everyone in the field remembered. Announcing too early risked credibility. Waiting too long risked someone else analyzing the publicly available Webb data and publishing first. They settled on a middle path. The team would present the results at a conference in September, not as a confirmed planet, as a candidate. A tantalizing, high-confidence candidate that required follow-up observations to verify. The abstract was carefully worded. It described S1 as a faint point source detected at 1.5 arcseconds from Alpha Centauri A, consistent with a planetary mass object in the system. Consistent with, not confirmed as. The language mattered. The exoplanet community has seen too many candidates turn into embarrassments. Caution was warranted. Word leaked anyway. By late August, rumors were circulating on astronomy Twitter. Someone had posted a speculative thread about unusual director's discretionary time observations Webb had conducted. Someone else had noticed that Alpha Centauri showed up in the public observation logs. The pieces weren't hard to connect. A few journalists started reaching out to team members for comment. Most declined. A few offered carefully worded non-denials. "We're analyzing interesting data. We'll have more to say soon." The hype began to build before the team was ready for it. The preliminary characterization, the mass estimate, the temperature, the orbital distance, all of it was based on assumptions. The team assumed S1 was reflecting light from Alpha Centauri A like a normal planet. They assumed its infrared brightness came from a combination of reflected starlight and thermal emission from its own interior. They assumed it wasn't a background object, a brown dwarf, or some exotic astrophysical phenomenon nobody had thought of yet. All of those assumptions were reasonable. None of them were proven. To prove them, the team needed more data. They needed to observe S1 again, months or years later, and confirm that it had moved along the expected orbital path. They needed to take a spectrum, splitting the planet's light into its component wavelengths to identify what molecules were present in its atmosphere. They needed to rule out with absolute certainty that the signal wasn't an artifact of the data processing. One way to do that would be to observe Alpha Centauri A with a different instrument, Webb's IR-CAM, the near-infrared camera, could image the same region at shorter wavelengths. If S1 showed up in IR-CAM images at the expected position, that would be strong confirmation. If it didn't, that would be a problem. Another option was ground-based follow-up. The extremely large telescope under construction in Chile would have the resolution to image planets around Alpha Centauri once it came online in the late 2020s. Other large telescopes, like the Very Large Telescope already operating in Chile, had advanced adaptive optics systems that could, in theory, reach the contrast levels needed to detect S1. Ground-based confirmation would be gold standard. It would eliminate any possibility that the detection was unique to Webb's optics or data pipeline. But ground-based telescopes had been trying to image planets around Alpha Centauri for decades. None had succeeded. The system was too bright, too close, too messy. If S1 was real, it was sitting at the absolute edge of what current ground-based instruments could detect. Confirming it from the ground would require perfect seeing conditions, perfect weather, perfect timing, and a bit of luck. The safer bet was another Webb observation, and that would have to wait. Webb's schedule is determined years in advance. Every hour of telescope time is competed for, reviewed, and allocated through a process that makes academic tenure decisions look simple. Getting a follow-up observation approved would require writing a new proposal, submitting it to the Time Allocation Committee, and convincing them that the initial detection was strong enough to justify more director's discretionary time or a slice of the regular observing cycle. That process takes months. The earliest the team could realistically expect another observation was mid-2025, maybe later, which meant the world would have to wait. The detection was real, the signal was strong, the analysis was solid. But solid isn't the same as certain, and in astronomy, certainty requires time. Time to watch the planet move, time to gather more photons, time to rule out every alternative explanation, no matter how unlikely. The team prepared their presentation for the September conference. They prepared for questions. They prepared for skepticism. What they didn't prepare for, what nobody could have prepared for, was what would happen when they pointed Webb at Alpha Centauri A again. Because when that moment came, when the telescope swung back toward the system and took another set of images, the signal that had been so clear, so obvious, so impossible to miss in August, was gone. The planet had vanished. The follow-up observation was scheduled for February 2025, 6 months after the initial detection. Long enough for S1, if it was real, to have moved noticeably along its orbit. Long enough for the team to have written up their preliminary findings, submitted them for peer review, and started planning the confirmation campaign that would turn a candidate into a discovery. 6 months is an eternity in the news cycle, but barely a blink in the timeline of a planet that had been orbiting its star for billions of years. The object wasn't going anywhere. It would be there when Webb looked again, except it wasn't. The observation executed on schedule. Webb pointed at Alpha Centauri A, aligned the coronagraph, and took the same sequence of exposures the team had used in August. Same instrument, same wavelength, same exposure times, same everything. The only variable was time. 6 months had passed. The stars had moved slightly in their mutual orbit. Earth had moved a quarter of the way around the Sun, shifting Webb's vantage point by hundreds of millions of kilometers. And S1, if it existed, had traveled roughly a sixth of the way around its orbit, sweeping through an arc of about 60 degrees as viewed from Earth. The data came down on February 14th, Valentine's Day. Kevin Wagner pulled up the files and started the processing routine. Calibration, alignment, reference subtraction. He'd done this 100 times by now. The August detection had been analyzed, reanalyzed, checked by independent teams, presented at conferences, and written up in a draft paper that was sitting with the journal editors waiting for confirmation before publication. Everyone on the team knew where S1 was supposed to be. The orbit simulations gave a predicted position. Not exact, because 6 exposures over a few hours isn't enough to nail down an orbit perfectly, but close. The planet should be sitting somewhere within a few arcseconds of Alpha Centauri A, offset by a slightly different angle than it had been in August. Wagner ran the subtraction. The image came up on his screen. Clean, too clean. No scattered light, no residual artifacts. No bright blob sitting where S1 was supposed to be, just flat grey noise. He stared at it for a long time. Then he ran the subtraction again with different reference images, still nothing. He adjusted the noise filtering, making it less aggressive so that faint signals would come through. The image got noisier, but no brighter spot appeared. He checked the observation logs to make sure the telescope had actually pointed at the right coordinates. It had. He checked the coronagraph alignment. Perfect. He checked whether Alpha Centauri B had contaminated the field more than expected. It hadn't. Everything about the observation had worked exactly as planned. The planet was gone. Wagner sent a message to the team. 3 words: "We have a problem." Over the next 72 hours, the analysis went from confusion to something closer to panic, not the loud kind, the quiet kind, the kind where you start questioning whether you made a catastrophic mistake 6 months ago and are only now finding out. The team pulled the August data back out and re-examined it from scratch. Was the signal real? Had they missed something? Had the entire detection been an artifact they'd convinced themselves was a planet because they wanted it to be a planet? They ran every test again, checked the alignment, checked the subtraction, checked whether the signal could have been caused by a hot pixel that happened to be in the right place at the right time. It wasn't. The August signal was still there, still clear, still sitting in the same spot across 6 independent exposures. It passed every statistical test. It looked, by every objective measure, like a real astronomical object. The February data was also clean, no obvious problems, no instrument glitches, no data corruption. The observation had simply failed to detect anything at the expected position. There are a few ways this can happen. The first and most embarrassing possibility is that the original detection was never real, a false positive, some combination of noise, optical artifacts, and wishful thinking that created the appearance of a planet where none existed. It happens more often than astronomers like to admit. You stare at noisy data long enough, your brain starts seeing patterns. You run enough statistical tests, and eventually one of them will give you a significant result by pure chance. The August detection had been strong, 5.5 sigma, meaning the probability of it being random noise was less than 1 in a million. But 1 in a million is not 0. And when you're looking at data from the brightest nearby star system using a telescope that's never been used this way before, the usual rules about statistical significance start to bend. The team didn't believe it was a false positive. The signal had been too clean, too consistent across multiple exposures, but they couldn't rule it out. Not yet, not until they understood why it had disappeared. The second possibility was instrument error. Something about Webb's coronagraph or detector that produced a ghost signal in August and didn't repeat in February. Telescopes are not perfect. They have quirks. Hubble famously launched with a mirror that was ground to the wrong shape, a mistake that wasn't discovered until after it reached orbit. Webb had survived its deployment without any major issues, but that didn't mean it was flawless. Coronagraphs are especially finicky. They rely on precise alignment between the mask and the star's image. Drift by a fraction of a pixel, and the suppression pattern changes. Light leaks through in unexpected ways. The team checked the coronagraph telemetry from both observations. Everything matched. The mask had been in the same position, the alignment was identical, the optical path was clean. If there was an instrument problem, it was subtle enough that the diagnostics hadn't caught it. The third possibility, the one nobody wanted to say out loud, was that S1 was real but had physically moved to a position where Webb couldn't see it. Not because it had left the system, because it had moved too close to the star. Alpha Centauri A is bright, absurdly bright. Even with a coronagraph suppressing its light by a factor of 10,000, there's still a region immediately around the star where no planet, no matter how large, can be detected. The scattered light is too intense, the diffraction halo too wide. Anything sitting within about 1 arc-second of the star gets drowned out. That exclusion zone, in physical terms, translates to roughly 0.7 astronomical units at Alpha Centauri's distance. If S1's orbit brought it inside that radius at any point, it would disappear from Webb's view for part of its orbit, reappear when it swung back out, disappear again on the next pass. The team pulled up the orbit simulations they'd run after the August detection. Most of those orbits were circular or nearly circular, keeping the planet at a steady 1 to 1.5 astronomical units from the star. Safe, always visible, but some of the possible orbits were elliptical, long stretched ovals that brought the planet much closer to the star at certain points in its trajectory. If S1 was on one of those elliptical orbits, and if February happened to catch it near the closest point, Webb wouldn't have been able to see it. The planet would still be there, just hidden. Sangi, one of the team members who specialized in orbit fitting, started running simulations. He took the 6 August detections, which gave S1's position and approximate velocity, and calculated every possible orbit consistent with that data. Thousands of them, some circular, some elliptical, some tilted relative to our line of sight. For each orbit, he projected where the planet would be in February and whether Webb would have been able to detect it. The results were unsettling. In about half of the simulated orbits, S1 moved too close to Alpha Centauri A between August and February, too close for Webb to separate it from the star's glare. The non-detection wasn't just possible, it was expected for a significant fraction of the parameter space. That should have been reassuring. It meant the disappearance could be explained without invoking false positives or instrument errors. The planet was still there, just hiding. But it also meant the team couldn't confirm anything. If S1 was on an elliptical orbit, it might not be visible again for months, maybe a year, maybe longer. The timing depended on details they didn't have: the eccentricity of the orbit, the orientation of the orbit relative to Earth, the exact position of the planet when Webb happened to be looking. All unknowns. The February non-detection leaked almost as fast as the August detection had. Someone posted a vague tweet. Someone else replied with speculation. A journalist reached out to one of the team members and got a carefully worded response that confirmed the follow-up observation had occurred but declined to comment on the results. That was enough. Within days, the story shifted from Webb finds planet around Alpha Centauri to Webb's Alpha Centauri planet mysteriously vanishes. The second headline was better for clicks, worse for the team's reputation. Charles Beischmann, who had praised the August detection as a remarkable technical achievement, was more cautious when asked about the February result. "Direct imaging is hard," he said in an interview. "You're looking for something incredibly faint next to something incredibly bright. Sometimes you think you see something and it turns out to be noise. Sometimes you really do see something, but then it moves and you can't find it again. That's not a failure of the method. That's just the reality of how this kind of science works." Other astronomers were less diplomatic. A few pointed out that the 2012 Alpha Centauri B planet had followed a similar trajectory. Initial detection, headlines, excitement, follow-up observations that failed to confirm, eventual retraction. The comparison stung because it was a apartment the Alpha Centauri system had burned researchers before. It was starting to feel like the system was cursed. Every time someone claimed to find a planet there, the planet evaporated under scrutiny. The team pushed back. This was different. The August signal was stronger than the 2012 detection. The data quality was better. The analysis was more rigorous. But none of that mattered if they couldn't find the planet again. They scheduled another observation for April 2025, 2 months after the February attempt. Not long enough for S1 to move dramatically if it was on a multi-year orbit, but long enough that its position would shift by a few degrees. If the planet was real, and if it was on one of the orbits that kept it visible most of the time, April might catch it. The observation was approved. Webb pointed at Alpha Centauri A again on April 18th. The data came down 3 days later. Wagner processed it immediately. He didn't wait. He didn't double-check the calibration. He just ran the subtraction and looked. Nothing. Still nothing. The same flat grey field. The same absence of signal. No bright blob. No faint smudge. No hint that anything had ever been there. 3 observations. 1 detection. 2 non-detections. That was the scorecard as of late April 2025, and the team had to decide what it meant. The simplest explanation was that S1 had never existed. The August detection was a fluke, a statistical accident, a combination of noise spikes that happened to align in a way that looked like a planet. The team would retract the candidate, issue a correction, and move on. Embarrassing, but not unprecedented. Science is full of retracted detections. The field moves forward. The problem with that explanation was that it didn't fit the data. The August signal was too strong, too consistent, too well-behaved. False positives don't usually show up in 6 independent images at the same position with the same brightness. They show up in one image and disappear in the next, or they move randomly, or they fail basic sanity checks. S1 had passed every test. Calling it a false positive required assuming that something extraordinarily unlikely had happened. Not impossible, just unlikely enough that it felt like giving up. The second explanation was that S1 was real but on an orbit that made it visible only rarely. Maybe it was on a highly elliptical orbit that kept it hidden most of the time. Maybe it was on a circular orbit but tilted at an angle that placed it behind the star during the February and April observations. Maybe there was something about the geometry of the system, the position of Alpha Centauri B, the scattered light environment that made detection possible in August and impossible afterward. The team ran more simulations, more orbit fits, more statistical tests. The results were ambiguous. Some orbits fit the data, some didn't. None of them could be ruled out definitively. The third explanation was the one nobody wanted to consider seriously. That S1 was real, but something had happened to it. Not in the sense that it had exploded or been ejected from the system. Nothing that dramatic, but something subtle. Maybe the planet had passed through a debris field and was temporarily surrounded by a cloud of dust that scattered its light, making it dimmer than expected. Maybe it had a highly variable atmosphere that changed its brightness on short timescales. Maybe it was something exotic, a rogue planet that happened to be passing through the Alpha Centauri system in August and was gone by February. That last option was absurd. Rogue planets don't conveniently line up with nearby star systems and then disappear on cue. But absurd doesn't mean impossible, just improbable. And when you've ruled out the probable explanations and still don't have an answer, improbable starts to look more appealing. The team didn't announce a retraction. They didn't announce confirmation either. They did what scientists do when the data refuses to cooperate. They wrote a paper, a careful, cautious, thoroughly hedged paper that presented the August detection, described the follow-up non-detections, laid out the possible explanations, and concluded with the academic equivalent of a shrug. The abstract used phrases like candidate planetary mass companion and requires further observations to confirm. The conclusion noted that the non-detections were consistent with a subset of possible orbital configurations, but do not allow for definitive confirmation or rejection of the initial signal. Translation: we found something, we can't find it again, we don't know what that means, and we need more data. The paper was submitted to the Astrophysical Journal Letters in May 2025. It passed peer review in July. The reviewers were skeptical but fair. One of them noted that the detection threshold and follow-up strategy represent the state-of-the-art for direct imaging of nearby stellar systems, but added that the non-detections raise legitimate questions about the robustness of the initial signal. Another reviewer was more blunt. Either the candidate is on an unusually unfavorable orbit or the detection was spurious. Additional observations are necessary to distinguish these scenarios. The paper was accepted for publication in August 2025, exactly 1 year after the original detection. By the time the paper came out, the initial excitement had faded, the media had moved on, other discoveries had taken center stage. Webb had found a dozen other exoplanets, some of them closer, some of them more exotic, all of them more reliably detected. The Alpha Centauri candidate became a footnote, a cautionary tale about the limits of direct imaging, a reminder that detecting a planet once is not the same as confirming it exists. But the team didn't move on. They kept analyzing the August data, kept running simulations, kept thinking about what they'd seen and where it had gone. Because if S1 was real, if the detection wasn't a fluke, then the disappearance meant something. It meant the planet was hiding, and if they could figure out where it was hiding, they could find it again. All they needed was time, and one more chance to point Webb at the right patch of sky at the right moment. The next observation window opened in August 2026, 2 years after the original detection, long enough for S1, if it was on a 1 to 2 year orbit, to have completed a full revolution and returned to roughly the same position it had been in when Webb first spotted it, long enough for the scattered light environment to reset, long enough for whatever combination of geometry and timing had made the planet visible in August 2024 to line up again. The team submitted a proposal for director's discretionary time, again. The proposal was approved, again. Webb would point at Alpha Centauri A one more time, and this time the entire exoplanet community would be watching. Because if S1 showed up again in the same place, at the same brightness, moving along the orbit the simulations predicted, then the mystery would be solved. The planet was real. It had always been real. It had just been playing hide and seek. And if it didn't show up, then the conversation would shift from whether the planet existed to what the August signal actually was, and why, after billions of years of quietly orbiting its star, it had chosen that specific week in August 2024 to make itself visible to the most advanced telescope humanity had ever built before disappearing without a trace. The team spent the summer of 2025 doing what scientists do when the universe refuses to make sense. They checked everything, again, and then they checked it a third time. Not because they thought they'd made a mistake, because they needed to be absolutely certain they hadn't before they started entertaining explanations that sounded like science fiction. First, they went back to the instrument telemetry. Every observation Webb conducts generates diagnostic data, temperature readings from the detectors, voltage levels in the electronics. The exact position of every motor that moves the mirrors and masks. The team pulled the logs from all three observations, August 2024, February 2025, and April 2025, and compared them line by line. They were looking for any deviation, any hint that something about Webb's coronagraph or detector had behaved differently in August than it had in the follow-up observations. They found nothing. The telescope had performed identically in all three cases. Same alignment precision, same thermal stability, same optical configuration. If the August detection was an artifact of the instrument, the artifact should have repeated. It didn't. Next, they examined the possibility of stellar contamination. Alpha Centauri B, the companion star, sits close enough to A that its light bleeds into the field of view even with careful masking. The team modeled the scattered light contribution from B at the time of each observation. The stars orbit each other every 79.9 years, and their separation as viewed from Earth changes throughout that cycle. In August 2024, the two stars were separated by about 7 arcseconds. In February and April 2025, they were slightly closer, about 6.5 arcseconds. That difference was real, but it was small, too small to account for the disappearance of a signal as strong as S1 had been. The scattered light models showed that B's contribution to the noise floor had increased by roughly 15% between August and the follow-up observations. 15% more noise should have made the planet harder to detect, not impossible. Unless the planet had been right at the edge of detectability in August, which it hadn't been. The signal had been clear, 5.5 sigma above the noise. You don't lose a 5 sigma signal to a 15% increase in background. Then they checked the data processing pipeline. Coronagraphic imaging relies on subtracting reference images from target images to remove the star's scattered light. The subtraction algorithm matters. Different approaches, different noise filtering strategies, different ways of aligning the images before subtraction, all of it can change what you see in the final result. The team reprocessed the August data using half a dozen different algorithms, some optimized for point source detection, some optimized for artifact rejection, some designed to be maximally conservative, erasing anything that didn't show up in multiple independent exposures. Every single algorithm found S1 in the August data, not in slightly different positions, in the same position, with the same brightness. The detection was robust to the choice of processing method. That ruled out the possibility that the team had inadvertently created the planet through some quirk of how they'd analyzed the images. By early fall, they'd eliminated every conventional explanation for the disappearance. The instrument hadn't malfunctioned. The star hadn't contaminated the field in some unexpected way. The data processing hadn't introduced a spurious signal, which left two possibilities. Either S1 was a real planet on an orbit that made it temporarily undetectable, or it was something else, something that wasn't a planet in the way astronomers normally use the word. Something that could appear in August, sit still long enough to be photographed 6 times, and then vanish by February without leaving a trace. That's when Sangi started running simulations with a different set of assumptions. Up until that point, every orbit model the team had tested assumed S1 was a stable, long-lived object, a gas giant that had been circling Alpha Centauri A for billions of years and would continue circling it for billions more. That assumption is baked into how astronomers think about planets. Planets don't just appear. They don't flicker in and out of existence. They're massive, gravitationally bound objects moving along predictable trajectories. If you detect one, it should still be there the next time you look, unless its orbit carries it behind the star or too close to the glare. It should be visible every time. Sangi asked a different question. What if S1 wasn't stable? What if the object the team had detected in August wasn't a planet at all, at least not in the traditional sense, but something transient, something that existed briefly and then stopped existing or stopped being detectable for reasons that had nothing to do with orbital mechanics? The idea felt wrong. Planets are permanent. That's what makes them planets. But Sanghi had been working in exoplanet direct imaging long enough to know that wrong-feeling ideas are sometimes the only ones that fit the data. He started digging into the literature on transient phenomena in planetary systems. Turns out astronomers have been theorizing about transient planets for decades, not because they've seen any, because the math allows for them. In the early solar system, during the chaotic phase when planets were still forming, collisions were common. Protoplanets, objects massive enough to be round but not yet settled into stable orbits, smashed into each other regularly. Some of those collisions resulted in mergers. The two objects stuck together and became one larger object. Some resulted in disruptions. The smaller object shattered, scattering debris across the system, and some resulted in ejections. The collision imparted enough velocity to one or both objects that they were flung out of the system entirely, becoming rogue planets drifting through interstellar space. None of those processes are transient in the sense that the object disappears. The mass goes somewhere. It just stops being a planet in the place you were looking. But there's another class of transient phenomena that's subtler. It involves not the destruction of a planet, but the temporary obscuration of one. If a planet passes through a dense debris field, a cloud of dust and ice left over from a recent collision or a comet breakup, that debris can scatter the planet's light. Not block it entirely, just diffuse it. Spread the infrared glow out over a larger area so that instead of a bright point source, you see a faint extended smudge that blends into the background noise. From a telescope's perspective, the planet effectively vanishes. It's still there, still orbiting, still warm. But it's no longer detectable as a discrete object. Wait for the planet to move out of the debris cloud, and it reappears, clear and bright, and exactly where orbital mechanics says it should be. Sanghi ran models of what that would look like in Webb's data. He simulated a Saturn-mass planet at 1 to 2 astronomical units from Alpha Centauri A, moving on a mildly elliptical orbit. Then he added a debris cloud, not a uniform disk like you'd find in a mature planetary system, a clump. A localized concentration of dust and ice sitting in one part of the orbit, dense enough to scatter infrared light, but not so dense that it would show up as a bright source in its own right. He tuned the parameters until the simulated planet appeared as a clean point source when it was outside the debris cloud and disappeared into the noise when it passed through. Then he checked whether the timing worked. Could S1 have been outside the cloud in August 2024 and inside it by February 2025? The answer was yes. If the debris cloud occupied roughly 15 to 20 degrees of arc along the planet's orbit, and if S1 happened to be just outside that arc in August, it would take about 3 to 4 months for the planet to move into the cloud. February would catch it right in the middle. April would catch it still inside. And by August 2026, a full orbital period later, the planet would have moved through the cloud and come out the other side. Visible again, right where it started. The model was elegant. It explained everything: the detection, the disappearance, the predicted return, but it had a problem. Debris clouds that dense, localized enough to obscure a planet for months but sparse enough not to glow brightly in the infrared themselves, are not common. They require a recent disruption, a collision or a breakup that happened within the last few thousand years, maybe the last few 100,000, long enough ago that the debris has spread out into a diffuse cloud, recent enough that it hasn't dissipated entirely. You don't find clouds like that in mature planetary systems. You find them in young systems, still undergoing the final cleanup phase of planet formation, or in systems that have been recently disturbed by something, a passing star, a rogue planet swinging through, an impact event large enough to shatter a moon or a large asteroid. Alpha Centauri A is not young. The star is about 6 billion years old, older than our Sun. Its planetary system, if it has one, should have finished forming billions of years ago. The era of giant collisions, the phase when debris clouds were common, ended long before multicellular life appeared on Earth. Finding an active debris cloud around Alpha Centauri A would be like finding a construction site in a neighborhood where all the houses were built in the 1950s. Not impossible, just surprising, and it would beg the question of what caused the disruption. Kevin Wagner, reviewing Sanghi's simulations, pointed out another issue. If S1 was moving through a debris cloud, Webb should have detected that cloud directly. Dust and ice warmed by the star glow in the mid-infrared, not as brightly as a planet, but brightly enough that Webb's mid-infrared instrument would have picked it up as diffuse emissions spread across the field. The team went back to the August images and looked for exactly that. They adjusted the brightness scaling to make faint extended structures visible. They ran edge detection algorithms designed to highlight gradients in the background. They checked whether any of the reference images used for subtraction might have accidentally removed a real cloud along with the starlight. They found nothing, no diffuse glow, no extended emission, no sign that a debris cloud existed anywhere near S1's position. If the planet was moving through dust, the dust was either colder than expected, less reflective than expected, or not there at all. That left one other possibility. The transient wasn't the debris, it was the planet itself. Not in the sense that S1 had been destroyed, in the sense that its brightness had changed. Planets don't usually do that. They're not stars, they don't flicker. Their thermal emission, the infrared glow that Webb detects, comes from heat stored in their interiors, left over from formation and supplemented by radiation absorbed from the star. That heat leaks out slowly over billions of years. The rate of leakage is steady. A gas giant at a given distance from a given star has a predictable temperature, and that temperature doesn't change much over human timescales. Jupiter's infrared brightness today is essentially the same as it was a century ago, the same as it will be a century from now. Planets are thermally stable, unless they're not. In 2019, a team of astronomers reported the discovery of a brown dwarf, an object halfway between a planet and a star that varied in brightness by more than a factor of 2 over the course of a few hours. The variations were caused by weather, massive storm systems rolling across the object's surface, exposing hotter, deeper layers and then covering them again as the storms evolved. Brown dwarfs are warmer than planets, and their atmospheres are more dynamic, but the same principle applies. If you have a thick atmosphere with active convection, you can get brightness variations, not over billions of years, over days or months. The team started modeling what would happen if S1 had a variable atmosphere, a gas giant with a weather system so extreme that its infrared brightness could change by a factor of 5 or 10 over the course of a few months. That kind of variability is absurd for a cold planet sitting 2 astronomical units from its star. Weather systems on Jupiter don't make Jupiter's global brightness flicker. They redistribute heat, but the total energy output stays roughly constant. To get the kind of variability that would make S1 disappear, you'd need something more dramatic than weather. You'd need an event, an atmospheric disruption that temporarily changed the planet's thermal structure. Maybe a massive volcanic eruption on one of the planet's moons, dumping enough dust into the atmosphere to block outgoing infrared radiation. Maybe a collision with a large asteroid that vaporized on impact and filled the upper atmosphere with a reflective haze. Maybe a tidal heating pulse, triggered by the planet passing close to Alpha Centauri A on an eccentric orbit, that dumped a surge of internal heat into the atmosphere and then faded over the course of weeks. None of those explanations felt satisfying. They required invoking rare events that just happened to occur in August 2024 and then conveniently stopped by February. The timing was too perfect. If S1 was variable, if it flickered on timescales of months, it should have been flickering for billions of years. And if it had been flickering, the August detection should have been preceded by earlier detections. Ground-based telescopes had been monitoring Alpha Centauri for decades. Hubble had looked at it. Other infrared surveys had swept across the system. None of them had reported anything like S1. The object either hadn't been there, or it had been too faint to detect. If it was too faint to detect before August 2024, why had it suddenly brightened? What changed? Sanghi proposed a different model. What if S1 wasn't a stable planet at all, but a recently formed one? Not recently in the sense of thousands of years, recently in the sense of millions. Planet formation doesn't stop the moment a gas giant reaches its final mass. The process winds down. The protoplanetary disk dissipates. Accretion slows, but for a few million years after the main growth phase, the planet is still settling, still contracting, still radiating away the heat generated during its formation. During that phase, the planet is much brighter than it will be later. A young gas giant can be hot enough to glow visibly. As it ages, it cools, its brightness drops. Eventually it reaches a steady state where the only heat it radiates is the trickle of internal energy left over from formation, plus whatever it absorbs from its star. That process takes tens of millions of years for a Jupiter-sized planet, maybe longer for something smaller like Saturn. If S1 was in that transitional phase, if it was a planet that had formed relatively recently and was still cooling, its brightness could change noticeably over timescales of decades or centuries, not months, not fast enough to explain the August to February disappearance, but fast enough that observations separated by years might detect it at different brightness levels. The problem with that model was the same as before. Alpha Centauri A is old, 6 billion years. If S1 was only a few million years old, it had formed recently, extraordinarily recently. Billions of years after the star's protoplanetary disk should have disappeared. Where did the material come from? How does a gas giant form in a system that has no gas left? The answers kept looping back to the same uncomfortable place. Something unusual had happened at Alpha Centauri A. Something that didn't fit the standard models of planetary system evolution. Either a planet had formed far later than it should have, or a planet had been captured from somewhere else, or a planet had undergone some kind of catastrophic event that reset its thermal clock. All three options required invoking processes that aren't supposed to happen in systems this old, this stable, this ordinary. And yet one of them had to be true, because S1 had been there in August. The data was unambiguous, the signal was real, and by February it was gone. By late 2025, the team had written up 3 separate explanatory models in the draft paper. The orbital obscuration model, where the planet passed behind the star or moved too close to resolve. The debris cloud model, where the planet's light was scattered by a localized concentration of dust. And the intrinsic variability model, where the planet itself changed brightness for reasons that weren't yet understood. The paper didn't pick a favorite. It presented all 3, outlined the observational tests that could distinguish between them, and concluded that the August 2026 observation would likely settle the question. If S1 reappeared in the same position, moving along the predicted orbit, the obscuration model was correct. If it reappeared in a different position or with a different brightness, one of the other models might fit better. And if it didn't reappear at all, then the team would have to seriously consider the possibility that the original detection had been something else entirely, not a planet, not a brown dwarf, something transient that had existed for a brief moment and then stopped existing in any form Webb could detect. The reviewers didn't like the intrinsic variability model. One of them wrote in the margin of the draft that invoking unknown physical processes to explain a non-detection is not substantially different from admitting the original signal was spurious. Another noted that, while the authors have done commendable work ruling out instrumental and procedural errors, the lack of follow-up confirmation weakens the case for any interpretation that requires the object to be real. The criticism was fair. In science, you don't get credit for detecting something once, you get credit for detecting it twice. Until the August 2026 observation, the team was stuck in limbo. They'd found something extraordinary, they just couldn't prove it. Wagner, in interviews, framed the situation more optimistically. "Even if we don't understand why the planet disappeared," he said, "the fact that we detected it at all tells us something important. It tells us that planets can exist around Alpha Centauri A, that the system isn't barren, and it tells us that Webb has the sensitivity to image those planets directly, which means we can keep looking." He was right, but the statement had a defensive edge to it. The kind of edge you hear when someone is trying to salvage a win from what feels increasingly like a loss. The unsettling truth, the one the team didn't put in the paper because it sounded too speculative, was that S1 might represent a new class of object, not a stable planet, not a brown dwarf, not a debris cloud or an artifact, something in between. Something that exists temporarily in systems undergoing late-stage dynamical shifts, a gravitationally bound clump of gas and dust that looks like a planet for a few years or decades and then dissipates or collapses or gets ejected before it finishes forming. Astronomers have theorized about objects like that, quasi-planets, transient worlds, things that blur the line between planet and protoplanet and aren't quite either. Nobody has confirmed one because nobody has been able to watch a planetary system in enough detail over a short enough timescale to catch one forming and dissolving. Webb, for the first time, might have done exactly that. If that's what S1 was, the implications were staggering. It would mean planetary systems don't finish forming and then stay static. They keep evolving, keep churning, keep producing objects that come and go on timescales short enough that humans could, in principle, watch it happen. And it would mean that our understanding of what qualifies as a planet, of what counts as a stable member of a solar system, might need to be revisited. The paper was published in August 2025. The conclusion was cautious, carefully worded, and profoundly unsatisfying. The team had detected something. They couldn't explain what it was. They couldn't confirm it was still there. And they couldn't rule out the possibility that it had never been a planet in the first place. The only certainty was that in August 2026, Webb would point at Alpha Centauri A one more time. And whatever it found, or didn't find, would determine whether S1 went down in history as one of the most important exoplanet discoveries ever made, or one of the most embarrassing false alarms in the history of direct imaging. The stakes couldn't have been higher, and the entire field was holding its breath. The trouble with hunting for life in the universe is that we keep assuming the universe plays fair. We assume planets form in orderly systems, settle into stable orbits, and stay put for billions of years while chemistry does its slow, patient work. We assume habitable zones are fixed, predictable regions where temperatures allow liquid water to exist on a surface. We assume that if a planet sits in that zone long enough, life might appear, and we assume that once it appears, it stays. None of those assumptions survive contact with Alpha Centauri. If S1 is real, if the August 2024 detection wasn't a fluke or an artifact or a statistical accident, then the nearest Sun-like star system to Earth is not the stable, orderly neighborhood we thought it was. It's a shooting gallery. A gravitational demolition derby where planets can flicker in and out of detectability, where orbits shift on timescales short enough that human astronomers can watch it happen, and where the concept of a habitable zone stops being a useful predictor of anything. That realization, uncomfortable as it is, matters more for astrobiology than almost any other exoplanet discovery in the last decade. Because if the closest star system we can study in detail turns out to be chaotic, then chaos might be normal. And if chaos is normal, then life, assuming it exists anywhere beyond Earth, has had to evolve strategies for surviving in environments that don't sit still. Start with the habitable zone. The phrase gets thrown around constantly in exoplanet discussions, usually without much context. The habitable zone, sometimes called the Goldilocks zone because it's not too hot and not too cold, is the region around a star where a rocky planet with an atmosphere could theoretically maintain liquid water on its surface. For a Sun-like star, that zone sits roughly between 0.9 and 1.5 astronomical units. Earth is at 1 astronomical unit. Venus, at 0.7 astronomical units, sits just inside the inner edge. Mars, at 1.5 astronomical units, sits right at the outer edge. The zone isn't a guarantee of habitability. Venus is a hellscape. Mars is a frozen desert. But the zone defines the range of distances where the temperature is at least compatible with liquid water, assuming everything else about the planet, atmosphere, magnetic field, geological activity cooperates. Alpha Centauri A's habitable zone sits in roughly the same place. The star is slightly more luminous than the Sun, which pushes the zone outward a bit. The inner edge is around 1 astronomical unit. The outer edge extends to about 1.7 astronomical units. S1, if it exists, sits right in the middle of that zone. At roughly 2 astronomical units in some of the orbital models, it's near the outer edge. At 1 astronomical unit in others, it's near the inner edge. Either way, it's occupying prime real estate, the exact region where a rocky planet could, in principle, have oceans. Except S1 isn't a rocky planet, it's a gas giant, Saturn-mass, according to the models. Somewhere between 90 and 150 Earth masses, depending on which brightness estimate you trust. A planet that massive doesn't have a surface, not a solid one. If you tried to land on it, you'd fall through layers of hydrogen and helium until the pressure crushed you into a thin smear of organic molecules somewhere near the core. Gas giants don't host life the way terrestrial planets do. They don't have oceans in the sense that Earth has oceans. They have clouds, massive storm systems, layers of atmosphere so deep that temperature and pressure increase smoothly from near vacuum at the top to conditions hotter and denser than the interior of the Sun at the bottom. Nothing we'd recognize as life could survive there, but gas giants can have moons. Jupiter has 4 large ones. Saturn has 7. Some of them are bigger than Mercury. Some have atmospheres, some have subsurface oceans. Europa, orbiting Jupiter, has more liquid water beneath its ice shell than all of Earth's oceans combined. Enceladus, orbiting Saturn, has geysers that shoot water vapor into space from cracks in its surface. Both moons are considered potential habitats for life. not because they sit in the habitable zone, they don't, but because tidal heating from their host planet keeps their interiors warm enough to maintain liquid water despite being far from the sun. If S1 is real, and if it has moons, those moons could be habitable, not in the Goldilocks sense, in the tidal heating sense. A moon orbiting a Saturn-mass planet at 1 to 2 astronomical units from Alpha Centauri A would receive both starlight and tidal flexing. It would be warmer than Europa, possibly warm enough to have liquid water on its surface, not just beneath an ice shell. That's not speculation. That's orbital mechanics and thermodynamics. A large moon in that configuration is, by the standards of astrobiology, extraordinarily interesting. The problem is stability. Moons around gas giants in the habitable zone are only interesting if they stay there. If the planet's orbit is circular and stable, the moon orbits the planet in a predictable pattern, receiving a steady dose of starlight and tidal heating, and the environment stays consistent for billions of years. Consistent environments are where life has the best shot at appearing and evolving. Earth's environment hasn't been static. Climates shift, ice ages come and go, but the planet has stayed in roughly the same orbit for 4.5 billion years. The sun's brightness has increased by about 30% over that time, but the change has been gradual enough that life adapted. If Earth's orbit had been chaotic, if the planet had spent a few million years at 1 astronomical unit and then got kicked out to 2 astronomical units and then pulled back in, life would have had a much harder time, maybe an impossible time. S1's orbit, according to the models that fit the August detection and the subsequent non-detections, is not stable in the way Earth's orbit is stable. At least half of the simulated orbits that match the data are elliptical, elongated, bringing the planet as close as 1 astronomical unit to the star and pushing it as far as 2 astronomical units or more. That's a huge range. At 1 astronomical unit, a moon orbiting S1 would receive roughly the same amount of starlight as Earth. At 2 astronomical units, it would receive a quarter as much. The difference in temperature between those two extremes is the difference between a planet with liquid oceans and a planet where the oceans freeze solid. If S1's orbit is elliptical with a period of 1 to 2 years, any moon it hosts would experience wild climate swings on timescales of months. Summer at 1 astronomical unit, winter at 2. Summer again 6 months later. That kind of cycling doesn't give life much of a foothold. Worse, elliptical orbits in multi-star systems tend not to last. Alpha Centauri A and B orbit each other every 79.9 years. B's gravity tugs on anything orbiting A. Not enough to rip planets away immediately. Enough to perturb their orbits slowly over time. A planet on a circular orbit might stay circular for billions of years. A planet on an elliptical orbit gets tugged harder because its distance from the star changes, which changes how strongly it feels the tidal forces from the companion star. Those tidal forces can amplify the eccentricity, stretching the orbit further, or they can damp it, circularizing the orbit over time. Which outcome happens depends on the specific geometry of the system, the masses of the stars, the planet's initial orbit, and a dozen other variables. The point is that elliptical orbits in binary star systems are dynamically active, they evolve, and evolution in this context usually means either the orbit circularizes or the planet gets ejected entirely. If S1 is on an elliptical orbit, it might not stay in the habitable zone. It might already be leaving, not in the sense that it's been flung out of the system, in the sense that its orbit is shifting, drifting outward or inward over timescales of thousands or millions of years, driven by the cumulative gravitational kicks from Alpha Centauri B. The planet could spend a few million years in the habitable zone and then drift out. Spend a few million years in the outer system where it's too cold for liquid water. Drift back in, spend another few million years in the zone. That kind of flickering in and out of habitability on timescales of millions of years is long compared to a human lifetime, but short compared to the timescales life needs to evolve. On Earth, it took about 1 billion years for single-celled life to appear, another billion for multicellular life, another billion for complex animals. If Earth had spent half of that time outside the habitable zone, frozen solid, it's unclear whether the process would have completed. Maybe life is resilient enough to survive those interruptions. Maybe it isn't. Nobody knows because we only have one example. The existence of a Saturn-mass planet in Alpha Centauri A's habitable zone also raises questions about whether smaller planets could exist there. Gas giants don't form where we find them. Not usually. The standard model of planet formation says that gas giants form in the cold outer regions of a protoplanetary disk, beyond what's called the snow line, where water ice and other volatiles condense into solid grains. Those grains stick together, building up into larger and larger objects until one of them gets massive enough to start pulling in gas from the surrounding disk. Once that happens, the planet grows fast. It becomes a gas giant, but it forms far from the star, out where it's cold. Jupiter formed somewhere around 5 astronomical units from the Sun. Saturn formed around 10. Both are still roughly where they formed, though Jupiter has drifted inward slightly over billions of years. S1 is at 1 to 2 astronomical units. If it formed there, which is unlikely because that region is too warm for gas giants to form efficiently, then the protoplanetary disk around Alpha Centauri A must have been unusually dense or unusually cold. If it didn't form there, if it formed farther out and migrated inward, then it plowed through the inner system on its way in. Migration is common. Most of the gas giants we've found around other stars are hot Jupiters, massive planets orbiting extremely close to their stars, sometimes closer than Mercury is to the Sun. Those planets didn't form there. They formed farther out and migrated inward, driven by interactions with the protoplanetary disk or by gravitational scattering from other planets. When a gas giant migrates, it doesn't travel alone. It drags material with it. It scatters smaller planets. It ejects some. It swallows others. By the time the migration stops, the inner system is usually a mess. If S1 migrated inward to its current position, any terrestrial planets that formed in Alpha Centauri A's habitable zone before the migration would likely have been destroyed or ejected. The gas giant's gravity would have destabilized their orbits, flung some into the star, flung others out into interstellar space, left behind a few survivors on highly eccentric orbits that might or might not settle back into stable configurations over time. The solar system went through something similar early in its history. Jupiter and Saturn migrated, not dramatically, but enough to destabilize the asteroid belt and scatter debris throughout the inner solar system. That scattering triggered the Late Heavy Bombardment, a period about 4 billion years ago when Earth and the other terrestrial planets were pummeled by impacts. Some of those impacts delivered water, some delivered organic molecules. Some might have wiped out any early life that had started to appear. The bombardment eventually ended, the orbits stabilized, and life got a second chance. If Alpha Centauri A's system is currently undergoing something similar, if S1 is still in the process of settling into a stable orbit, then any terrestrial planets in the habitable zone are getting hammered. Life, if it exists, is not having a good time. The alternative is that S1 didn't form around Alpha Centauri A at all, that it's a captured planet. Rogue planets, gas giants that were ejected from their birth systems and now drift through interstellar space, are more common than most people realize. Estimates suggest there could be billions of them in the Milky Way. More rogue planets than stars. Most of them are invisible. They don't orbit a star, so they don't reflect light. They don't emit much heat because they've cooled over billions of years of drifting. You only detect them when they pass in front of a background star and cause a brief gravitational lensing event, or when they happen to pass close to a star system with planets and get captured. Capture is rare but not impossible. If a rogue planet drifts into a star system at the right velocity and the right angle, and if there's another planet or star nearby to absorb some of the kinetic energy through a gravitational interaction, the rogue can lose enough speed to become gravitationally bound. It settles into an orbit, usually an eccentric one because the capture process is chaotic. Over time, the orbit might circularize through tidal interactions with the star, or it might stay eccentric, or the planet might get ejected again during a subsequent close encounter with another object in the system. Captured planets don't stay captured forever. They're temporary residents. They spend a few million years in the system and then leave. If S1 is a captured rogue, its presence in Alpha Centauri A's habitable zone is a coincidence, a brief alignment that happened to occur at the exact moment humans developed the technology to detect it. The odds of that are low. Not impossible, just low. Low enough that invoking capture feels like special pleading unless there's evidence for it. There's no direct evidence. But the fact that S1 appeared in August 2024 and vanished by February 2025 is at least consistent with an object on a highly eccentric or even unbound orbit, an object swinging through the system, bright enough to detect for a few months as it passed through the habitable zone, and then gone. Not ejected in the sense of leaving the system entirely. Gone in the sense of moving to a position where Webb couldn't see it anymore. If the planet is on an unbound trajectory, if it's not gravitationally locked to Alpha Centauri A but just passing through, the August detection might be the only time anyone ever sees it. By August 2026, it could be too far from the star to detect, too faint, too distant, a ghost that appeared once and then faded into the noise. That scenario terrifies astrobiologists more than any other. Not because a rogue planet passing through Alpha Centauri is inherently scary, because it implies that stable planetary systems, the kind we've been assuming are the norm, might be the exception. If Alpha Centauri, the closest and most studied multi-star system within reach, turns out to host transient planets, planets that flicker in and out of the habitable zone on timescales of millions of years or less, then habitable zones might not mean what we thought they meant. They might not be stable refuges where life can take root and evolve over billions of years. They might be flickering windows, regions where conditions are right for liquid water temporarily, interrupted by long stretches where conditions are hostile. Life that evolves in those environments, if it evolves at all, would have to be extraordinarily resilient. It would have to survive freezing, survive thawing, survive impact bombardment from debris kicked up by the shifting orbits of giant planets, survive periods where the star's radiation flux changes because the planet's distance changes. That's not impossible. Extremophiles on Earth survive freezing, boiling, radiation, pressure extremes. But extremophiles are simple. Bacteria, archaea, single-celled organisms with minimal metabolic requirements. Complex life, the kind that builds ecosystems and food webs and eventually develops intelligence, requires stability, it requires time. Flickering habitable zones don't provide either. The concept of a flickering habitable zone also forces a rethink of how we prioritize targets for the search for life. For decades, the strategy has been to focus on stars with planets in the habitable zone and then study those planets in detail, look for biosignatures, oxygen in the atmosphere, methane, phosphine, chemical combinations that don't make sense unless life is producing them. The assumption has been that if a planet sits in the habitable zone for long enough, life might appear, and if life appears, it might produce detectable waste products. That assumption works if the habitable zone is stable. It breaks if the zone flickers. A planet that spends 10 million years in the habitable zone, then 10 million years outside it, then 10 million years back in, might never develop life at all. Or it might develop life during the first habitable phase and lose it during the frozen phase. Or it might develop life multiple times, each time starting over from scratch after a mass extinction event triggered by orbital shifts. Detecting biosignatures in that kind of system would require catching the planet at the right moment, during one of the habitable phases. Miss that window and you conclude the planet is sterile when it's actually just between phases. S1, assuming it's real, also pushes the boundaries of exoplanet classification in ways that make the field uncomfortable. The International Astronomical Union has a definition of what counts as a planet. It has to orbit a star. It has to be massive enough that its own gravity pulls it into a round shape, and it has to have cleared its orbit of other debris. That third criterion is why Pluto got demoted. Pluto shares its orbital space with thousands of other objects in the Kuiper belt. It hasn't cleared its orbit, therefore not a planet. The definition works fine for stable systems where orbits don't change. It gets murky when you start talking about objects on highly eccentric orbits that cross through multiple regions of a system, or objects that are temporarily bound to a star but might not stay bound, or objects that appear in one observation and disappear in the next. Does S1 count as a planet? It orbits Alpha Centauri A, probably. Its gravity has pulled it into a round shape, almost certainly. Has it cleared its orbit? Nobody knows, because nobody knows what its orbit is. If it's on a stable long-term elliptical orbit, then yes, it's a planet. If it's on a chaotic orbit that's going to eject it from the system in a few million years, then maybe it's a planet now but won't be later. If it's a captured rogue that's only temporarily bound to the star, then it's not a planet by the IAU definition because it didn't form in the system. Classifications that worked when we only had 8 examples, the planets in our solar system, start falling apart when you have thousands of examples spanning every possible configuration. The deeper point is that S1, whether it turns out to be a stable planet, a transient planet, a captured rogue, or an artifact, has already changed the conversation. It's forced astronomers to confront the limits of what direct imaging can detect and what it can't. It's forced astrobiologists to think seriously about habitable zones that don't stay habitable. And it's forced theorists to build models that account for dynamical chaos in systems that, by every surface measure, should be stable. Alpha Centauri A is not a young star. It's not a variable star. It's not surrounded by a dense debris disk or a massive protoplanetary cloud. It's a normal, middle-aged, sun-like star in a binary system that's been gravitationally stable for billions of years. If that kind of star can host a Saturn-mass planet that flickers in and out of detectability on timescales of months, then the universe is weirder, messier, and less predictable than any of the models anticipated. And if the universe is that messy, then life, assuming it's out there, has had to adapt to conditions that make Earth's relatively stable 4.5 billion year history look like a lucky exception rather than the rule. Which brings the conversation back to August 2026. One more observation. One more chance to point Webb at Alpha Centauri A and see whether S1 reappears in the same place it was in August 2024. If it does, the mystery is solved. The planet is real, its orbit is predictable, The disappearance was just a matter of bad timing and unfavorable geometry. If it doesn't, then the field moves into uncharted territory, and the implications for astrobiology and for our understanding of how planetary systems evolve become impossible to ignore. The calendar matters, not in the usual sense where one day bleeds into the next, and the only difference between Tuesday and Wednesday is what you decide to have for lunch. In the sense that there are specific moments in time when the geometry of the universe lines up in a way that lets you answer a question you couldn't answer yesterday and won't be able to answer tomorrow. August 2026 is one of those moments. Not because anything magical happens that month, because that's when Webb gets another clean shot at Alpha Centauri A, and if S1 is real, if the August 2024 detection wasn't a fluke or an artifact or a cosmic prank, then the planet should be back, sitting in roughly the same position relative to the star, moving along the same orbit, glowing with the same faint infrared light that made it visible 2 years earlier. If it's there, the mystery is solved. If it isn't, the mystery deepens into something nobody in the field is prepared to explain. The reason August 2026 matters has everything to do with orbital mechanics and almost nothing to do with the calendar humans invented to keep track of harvest seasons. S1, according to the models that fit the August 2024 detection, orbits Alpha Centauri A at a distance somewhere between 1 and 2 astronomical units. That translates to an orbital period of roughly 1 to 2 Earth years, closer to 1 year if the planet is at 1 astronomical unit, closer to 2 years if it's farther out. The exact number depends on details the team doesn't have yet. The planet's mass, its orbital eccentricity, the inclination of its orbit relative to our line of sight. All unknowns. But the range is solid, 1 to 2 years, which means that by August 2026, S1 will have completed at least 1 full orbit since the initial detection, possibly 2, and if the orbit is stable, the planet should return to the same patch of sky where Webb saw it in August 2024, not the exact same pixel. The star's position shifts slightly over time due to proper motion, and Webb's vantage point changes as it orbits the Sun, but close, within a few arcseconds, close enough that if Webb points at the right coordinates and takes the same sequence of exposures it took 2 years earlier, the planet should show up. That's the optimistic scenario, the one where everything works and the planet cooperates. The team has spent the last year planning for it. They've refined their orbital models, incorporated the constraints from the February and April 2025 non-detections, and narrowed down the range of possible orbits that fit all the data. Not all of those orbits bring S1 back into view by August 2026. Some keep the planet too close to the star, buried in the glare where Webb can't resolve it. Some place it at an angle where the scattered light from Alpha Centauri B contaminates the field too heavily for clean subtraction, but a significant fraction of the models, maybe 40%, predict that S1 should be visible in August 2026 if it's on a stable orbit, visible and detectable, bright enough to stand out above the noise, far enough from the star that the coronagraph can suppress the starlight without also suppressing the planet. The observation itself will look almost identical to the August 2024 sequence. Webb will point at Alpha Centauri A using MIRI, the mid-infrared instrument, because MIRI operates at wavelengths where the contrast between a warm gas giant and a sun-like star is most favorable. The coronagraph will block the star's light, creating an artificial eclipse that darkens the center of the field and lets the faint glow from anything orbiting nearby come through. The exposure time will be long, several hours, long enough to collect enough photons from a faint object that the signal rises above the detector noise. The telescope will take multiple exposures, shifting slightly between each one. so that the team can later subtract reference images and remove artifacts caused by the telescope's optics. Same strategy, same instrument, same wavelength. The only thing that changes is the date and the stakes. If S1 reappears, the detection becomes a confirmation, not just a candidate anymore, a real planet. The closest directly imaged gas giant to Earth, the first confirmed planet orbiting Alpha Centauri A, the kind of discovery that gets written into textbooks and mentioned in every intro astronomy class for the next 50 years, but confirmation alone doesn't solve the mystery. Because the planet still vanished between August 2024 and February 2025, still failed to show up in the April follow-up. A reappearance in August 2026 wouldn't erase those non-detections. It would contextualize them. It would mean the planet is real, but its visibility from Earth is intermittent. Sometimes it's in the right position to be seen, sometimes it isn't. The geometry matters, the orbit matters. The alignment of Webb's position relative to Alpha Centauri A and the planet's position relative to both of them, all of it has to line up. Miss that alignment by a few weeks or a few degrees, and the planet disappears from view even though it's still there, still orbiting, still glowing faintly in the infrared. That kind of intermittent visibility is not unprecedented. Exoplanets on highly elliptical orbits disappear and reappear all the time in radial velocity surveys. The signal comes and goes as the planet swings closer to and farther from the star, changing the star's wobble in ways that are easier or harder to detect, depending on the geometry. But radial velocity doesn't care where the planet is in the sky. It only cares about how fast the star is moving toward or away from Earth. Direct imaging is different. Direct imaging cares about everything. The planet's position, its brightness, the angle of its orbit, the scattered light from the star, and any companion stars nearby. The optical performance of the telescope, the quality of the reference images used for subtraction. Any one of those variables shifts, and the planet can vanish even though nothing about the planet itself has changed. If S1 shows up in August 2026, the team will immediately start analyzing the data to extract as much information as possible, not just confirming that it's there, measuring where it is, how bright it is, whether it's moved along the predicted trajectory, whether its infrared spectrum, the distribution of wavelengths in the light it's emitting, matches what you'd expect from a Saturn-mass gas giant at that distance from the star. Murray can take spectra, not as detailed as what you'd get from NIRISpec, Webb's dedicated spectrograph, but detailed enough to identify major atmospheric features: water vapor, methane, ammonia, carbon dioxide, the same molecules that show up in the atmospheres of Jupiter and Saturn. If S1 is a gas giant, its spectrum should look similar, not identical, because the planet is warmer and farther from its star, but similar enough that the comparison makes sense. Finding those spectral features would be the final confirmation, not just that the planet is there, that it's a planet, not a brown dwarf, not a background star, not some exotic astrophysical phenomenon masquerading as a planet, an actual gas giant with an atmosphere and a temperature consistent with its distance from Alpha Centauri A. The team is also planning to use NICAM, Webb's near-infrared camera, as a backup. NICAM operates at shorter wavelengths than MIRI, where the contrast between a planet and a star is worse, but it has higher spatial resolution, finer detail. If S1 is sitting close to the edge of Webb's detection limit, where MIRI barely picks it up, NIRISpec might not see it at all. But if the planet is brighter than expected, or if the scattered light environment is cleaner than the models predict, NIRISpec could provide an independent confirmation. 2 instruments, 2 wavelengths, 2 independent detections, that's the gold standard. That's what turns a candidate into a confirmed planet that nobody can argue with. The 2012 Alpha Centauri B planet didn't have that. It had one detection from one instrument analyzed one way. When other teams reanalyzed the data using different methods, the planet disappeared. S1 has already survived one round of reanalysis. The August 2024 signal held up under scrutiny from multiple independent teams. But one detection is still one detection. 2 would be better. 3 would be definitive. If the planet doesn't show up, the conversation shifts fast. The first question the team will ask is whether they pointed at the right place. Webb's pointing system is precise, but it's not infallible. If the coordinates were off by a fraction of an arc-second, the coronagraph might have been misaligned just enough to block the planet instead of the star, or the field of view might have shifted slightly, placing the planet outside the area Webb was imaging. Those kinds of errors are rare but not impossible. The team will check the telemetry, verify that the telescope pointed where it was supposed to point, verify that the coronagraph aligned correctly, verify that the exposure times matched the plan. If everything checks out and the planet still isn't there, the next question is whether the models were wrong. Maybe S1's orbit isn't what the team thought it was. Maybe the planet is on a longer period orbit, 2.5 years or 3 years instead of 1 to 2, and August 2026 catches it at a point where it's too close to the star or too far from the optimal viewing geometry. That's plausible. The initial detection gave the team a snapshot of the planet's position and velocity at one moment in time. Extrapolating that forward to predict where the planet will be 2 years later requires assumptions. Assumptions about the orbit's shape, assumptions about how the gravity of Alpha Centauri B perturbs that orbit, assumptions about whether the planet's brightness is constant or variable. Get any of those assumptions wrong, and the prediction fails even if the planet is real. The third possibility, the one nobody wants to say out loud but everyone is thinking about, is that S1 isn't a stable planet at all, that it's something transient, something that existed briefly in August 2024 and then stopped existing or stopped being detectable for reasons that current models don't account for. A captured rogue planet that swung through the system and kept going. A debris cloud from a recent collision that glowed brightly for a few weeks and then dissipated. A gravitationally bound clump of gas and dust that looked like a planet for a moment and then collapsed or evaporated before finishing its formation. Any of those explanations requires invoking processes that aren't supposed to happen in systems as old and stable as Alpha Centauri. But the data doesn't care what's supposed to happen, it cares what did happen. And if S1 doesn't reappear in August 2026, the field will have to confront the possibility that something genuinely weird occurred at Alpha Centauri A in the summer of 2024. Something that created a transient infrared source strong enough and stable enough to pass every artifact rejection test the team could throw at it. Something that looked exactly like a planet and then vanished. There's a fourth possibility that's even less comfortable, that the August 2024 detection was an artifact after all. Not a simple one, not a hot pixel or a cosmic ray or a glitch in the electronics, something subtle. A combination of scattered light, diffraction artifacts, and noise that happened to align in a way that produced a false positive strong enough to fool the analysis pipeline. The team has checked for that multiple times, using multiple methods. The signal passed every test. But tests aren't perfect. Statistical confidence isn't certainty. A 5 sigma detection means the probability of the signal being random noise is less than 1 in a million. 1 in a million is not 0. And when you're working at the absolute edge of what the telescope can detect, when you're looking for something 10,000 times fainter than one of the brightest stars in the sky, the usual rules about signal-to-noise ratios start to bend. Maybe the August 2024 observation hit that 1 in a million case. Maybe the team got unlucky in exactly the wrong way. If that's true, the non-detections in February, April, and August 2026 aren't telling them the planet moved or changed brightness. They're telling them the planet was never there. The signal was noise, and the entire story was a statistical accident. Nobody on the team believes that. But belief doesn't determine what the data shows, and if August 2026 comes back empty, belief won't matter. The field will move on. The candidate will be downgraded from promising to unconfirmed to likely spurious. The draft paper will be revised, the conclusions softened, the abstract rewritten to emphasize the challenges of direct imaging in binary star systems rather than the discovery of a new planet. The media will publish follow-up articles with headlines like "Webb's vanished planet remains missing" and "Alpha Centauri search ends in disappointment." And S1 will join the long list of exoplanet candidates that didn't survive follow-up. Not because the detection was fraudulent, not because the team made a mistake, because astronomy is hard. Because detecting planets around nearby stars is harder than detecting them around distant ones. Because the universe doesn't owe us clear answers, and sometimes the data refuses to cooperate no matter how carefully you analyze it. But there's another side to this, a scenario where S1 does reappear in August 2026, and the reappearance raises more questions than it answers. Say the planet shows up, same position, same brightness, moving along the expected orbit. Everything checks out. The team confirms it's real, publishes the result, and the discovery makes headlines. Then they take another look at the February and April 2025 data, the observations that failed to detect anything, and they realize something strange. The planet should have been visible in those observations too. The orbit models say it should have been far enough from the star and bright enough to detect. The geometry was fine, the scattered light environment was clean, and yet the signal wasn't there. Which means either the models are wrong in a way nobody has figured out yet, or the planet's brightness changed. Not gradually, abruptly, bright in August 2024, dim in February and April 2025, bright again in August 2026. That kind of variability doesn't fit any known model of gas giant atmospheres. Gas giants don't flicker like stars. They don't have internal fusion reactions that turn on and off. Their thermal emission comes from heat leaking out of their interiors, a process that runs steadily over billions of years. A planet that changes brightness by a factor of 10 over the course of a few months isn't behaving like a planet. It's behaving like something else. And if S1 is doing that, it's either the first example of a new class of object, or the detection was contaminated by something variable that isn't the planet itself. Either way, confirmation doesn't close the book. It opens a new chapter. The August 2026 observation will also tell the team something important about Webb's capabilities. The telescope has been operating for more than 4 years by that point. Long enough that the mirrors have collected a thin coating of micrometeorite dust, long enough that the detectors have accumulated radiation damage from cosmic rays, long enough that some of the fine alignment between the mirror segments has drifted slightly due to thermal cycling. None of those effects are catastrophic. Webb was designed to operate for at least 10 years, and it's performing well within specifications. But degradation is real. Instruments age, sensitivity decreases. The question is whether Webb in 2026 is still sensitive enough to detect S1 if the planet is there. The team has run simulations. They've modeled how dust accumulation affects the telescope's throughput, how radiation damage increases the detector noise, how alignment drift changes the point spread function. The results are encouraging. Webb should still be able to detect a Saturn-mass planet at 1 to 2 astronomical units from Alpha Centauri A with the same confidence level it had in 2024. Should, not guaranteed. Astronomy is full of observations that should have worked and didn't. The only way to know for sure is to point the telescope and collect the data. Ground-based telescopes are also getting involved. The extremely large telescope in Chile, scheduled to begin science operations in the late 2020s, will have the resolution to image planets around Alpha Centauri once it's fully operational. The ELT's mirror is 39 meters across, 6 times larger than Webb's, and while it operates in visible and near-infrared wavelengths where the contrast between a planet and a star is worse, its sheer size compensates. Adaptive optics systems can correct for atmospheric turbulence in real time, sharpening the image to the point where a gas giant at 1 astronomical unit from Alpha Centauri A should be resolvable. The ELT won't be ready in time for the August 2026 observation, but it will be ready for the next one, and the next one after that. If S1 is real, and if its orbit brings it back into a detectable position every year or two, the ELT will provide long-term monitoring that Webb can't. Webb is a space telescope. Its observation time is competed for by thousands of astronomers working on thousands of different projects. You don't get to monopolize it for a single target, no matter how important that target is. The ELT is different. It's a ground-based facility with enough observation time that long-term monitoring programs are feasible. If S1 turns out to be a variable planet, if its brightness or position changes on timescales short enough to track, the ELT will be the instrument that figures out why. There's also talk of using other space telescopes. Hubble, despite being decades old and operating well past its original design lifetime, still functions. Its cameras aren't as sensitive as Webb's and it can't see as far into the infrared, but it has a longer track record and a more stable pointing system. If S1 shows up in Webb's August 2026 data, Hubble could provide an independent check. Same target, different telescope, different wavelength. Concordance between the two would be strong evidence that the detection is real and not an artifact unique to Webb's optics. The European Space Agency's Gaia mission, which has been mapping the positions and motions of stars across the Milky Way since 2013, could also contribute. Gaia doesn't image planets directly, but it measures stellar wobbles with extraordinary precision. If S1 is massive enough and close enough to Alpha Centauri A, its gravity should cause the star to wobble slightly. Gaia's astrometric data might pick that up. The wobble would be tiny, measured in micro-arcseconds, but Gaia's precision is measured in micro-arcseconds too. A detection there would confirm S1's existence through an entirely independent method. No imaging, no spectroscopy, just the star's motion in response to an unseen companion. That kind of multi-method confirmation is as close to certainty as astronomy gets. The stakes go beyond Alpha Centauri. If S1 is real, it changes how astronomers think about nearby star systems. For decades, the assumption has been that the closest stars to the Sun are too well studied, too boring, to harbor major surprises. We've looked at them with every telescope we have. We've measured their distances, their masses, their compositions, their rotation rates. We've searched for planets using every technique available, and we've mostly come up empty. Proxima Centauri B is the exception, not the rule. The discovery of a gas giant around Alpha Centauri A would mean we missed something big. Something sitting in our astronomical backyard for billions of years while we looked right past it. That's humbling. It's also exciting because it means there's more to find. If the nearest Sun-like star has a Saturn-mass planet we didn't know about until 2024, what else is hiding in the data? What other planets are sitting just below the detection threshold, waiting for the next generation of instruments to pull them out of the noise. The August 2026 observation is not just about S1, it's about proving that direct imaging works. That coronagraphs and reference subtraction and all the complicated data analysis techniques astronomers have been developing for the last 2 decades can actually detect planets around the brightest, closest, most challenging targets in the sky. If Webb can do it at Alpha Centauri, it can do it anywhere. The technique scales, the methods generalize. Every star within 10 light-years becomes a potential target. Every Sun-like star within 20 light-years. The catalogue of directly imaged exoplanets, which currently numbers in the dozens, could explode into the hundreds within a decade. And with that explosion comes the ability to study those planets in detail, to take spectra, to map their atmospheres, to search for biosignatures on any moons they might host. To answer, finally, the question that's been driving this entire field since it began: are we alone? August 2026 is 17 months away as of the time this script is being written. Not long in the grand scheme of the universe, a blink, but long enough that the waiting feels interminable. Long enough that every press release about Webb, every new exoplanet discovery, every incremental advance in direct imaging techniques gets measured against the question nobody can answer yet. Will S1 be there when we look again? The team doesn't know. The models give probabilities, not certainties. 40% chance the planet is visible, 60% chance it isn't, or maybe 50-50, or maybe the models are wrong and the real probability is something else entirely. The only way to find out is to wait, to let the Earth complete another orbit around the Sun, to let Alpha Centauri A move through another fraction of its 79-year dance with Alpha Centauri B, to let Webb drift through its own slow orbit around the second Lagrange point, waiting for the moment when the geometry aligns and the observation becomes possible again, and then to point the telescope and see what the universe has to say, because the universe always gets the last word. Astronomers build models, make predictions, design observations, analyze data. They do everything right. And sometimes the planet is there, and sometimes it isn't. And sometimes the answer is something nobody predicted, something that forces a rethink of everything that came before. S1 might be that kind of answer, the kind that doesn't fit neatly into the boxes we've drawn, the kind that opens more questions than it closes, the kind that keeps astronomers awake at night, staring at data and wondering what they're actually looking at. August 2026 is coming. The telescope will point, the data will arrive, and then the world will know whether the planet that vanished without a trace was ever really there at all, or whether it's something stranger, something that defies every model, every expectation, every assumption about how planets behave and where they hide and why. After billions of years of silence, they choose one specific moment to show themselves before disappearing back into the noise. The answer is already written. Locked into the orbit S1 is following right now, this very second, as you read these words. We just have to wait for the light to reach us, and when it does, everything changes. So here's what we're left with: a signal that appeared once, a planet that vanished, a star system so close we can almost reach out and touch it, and yet so complicated that it refuses to give us a straight answer. August 2026 will tell us something. Maybe it will tell us the planet is real. Maybe it will tell us we were chasing noise. Or maybe, and this is the possibility that keeps circling back, it will tell us something we weren't prepared to hear, that planets don't always behave the way we expect, that the habitable zones we've been drawing on charts and using to prioritize our search for life are more like suggestions than rules, that the universe, even in our own neighborhood, even around the stars we've studied for centuries, still has the capacity to surprise us in ways that make us question whether we understood anything at all. The truth is, whether S1 reappears or stays hidden, the story has already changed us. It's forced astronomers to admit that detecting something once isn't the same as understanding it. It's forced astrobiologists to think about worlds that flicker in and out of habitability on timescales short enough that complex life might never get a foothold. And it's forced everyone watching to confront the uncomfortable reality that the closest star system to Earth, the one we've been staring at since Galileo first pointed a telescope at the sky, might still be keeping secrets. We built the most powerful telescope in history. We pointed it at our nearest neighbor. We found something extraordinary, and then it disappeared. That's not a failure. That's the universe reminding us that we're